Let me recall the definition of a limit. Let f from a to r be a function and x in r be a limit point of a. We say limit x going to, not x going to, y going to x, f of y equal to L in R if for each epsilon greater than 0 we can find delta greater than 0 such that if mod y minus x less than delta and y in a, then mod f of y minus f of x is less than epsilon, right? So this was the definition of a limit. We have I made a mistake. If 0 less than y minus x, modulus of y minus x less than delta. Remember, the reason why we put a 0 less than is to ensure that y is never equal to x. This is a definition of what happens to f as y approaches x but is never equal to x. Okay, I'm going to leave you with an exercise which is fairly easy because we have done the heavy lifting when we characterized the three possible definitions of continuity. Let limit y going to x, or rather let me state it in a different way. Limit y going to x f of y is equal to L if and only if for any sequence yn in A converging to x and yn is never x, then f of yn converges to L. Okay. Now again, one of the reasons why we took x to be a limit point and not just any adherent point is because there might not be any sequence satisfying the condition yn converging to x and yn not equal to x unless this point x is a limit point and not merely any old adherent point. Okay. So what this says is you can characterize limits of functions entirely using the notion of limits of sequences. And the proof of this involves a bit of work, but we have already done that work when we saw that the three definitions of continuity are equivalent. All you have to do is go through that proof thoroughly and write down a proof of this. So this is my strategy of forcing you to rewatch that lecture once more. Okay, now that this is done, we save a lot of effort in the next theorem on limit laws. Limit laws. Let f comma g from a to r be functions and x in a be a limit point. Same setup except now we have two functions. Then number one, limit I must also make one more hypothesis. Assume limit y going to x f of x equal to L, limit y going to x f of y equal to L, and limit y going to x g of y equal to m. Then number one, limit y going to x f plus minus g of y equals L plus minus m. 2. Limit y going to x c times f of y equals CL, where C in R is fixed. Number 3. Limit y going to x f g of y, the product, is equal to Lm. And finally, limit, I need to put one more condition. If m is not equal to 0, then f divided by g is well defined for some bxr intersect A. If m is not 0, that is the limit of x y going to x of g of y is not 0, then f divided by g is actually well defined for some r greater than 0. Okay, so let me just write this precisely. Then for some r greater than 0, the function g of y is not 0 whenever y belongs to B XR intersect A, which I just defined to be this B, which I defined to be this set B. Then X is a limit point of B and limit y going to x f of x by g of x. This is defined on B. Is equal to L by M. A bit wordy, but I want it to be a bit precise. All I want to say is, if the limit of the denominator is not 0, then when you are sufficiently close to the limit point x, the function itself is not 0. Therefore, you can define the quotient f by g on some ball bxr intersect A, which I am calling the set B. So I am taking the limit of this function defined on B at the point x. To do this, x must be a limit point. That is part of the statement, and that limit is equal to L by M. Okay. Now proof. Left to you. This might sound a bit harsh. I'm leaving everything for you, but everything follows directly from the fact that functional limits are completely characterized by sequences. All of these proofs follow immediately by applying the previous theorem, the previous exercise, which again I have left for you as an exercise. Everything follows immediately from this and the corresponding theorem for sequences. Now, I recommend that you don't waste your time writing out this entire proof in full detail. Rather, write a complete proof of the last part. Write a complete proof by yourself. Prove this fully. If you can do this last part, the other 3 will be a piece of cake. Okay. So the limit laws follow immediately just from the fact that we have already done the work for sequences. Now immediately we get nice consequences. Examples. X bar n is continuous at all points of R. This follows by the fact that X is continuous and 1 of the previous theorem, right? Not 1, 3 of the previous theorem. We have already shown that the function x is continuous. Now we have to show that x bar n is continuous. The previous theorem will do the job for us. Excellent. Yet another thing, look at a polynomial, which we call is an expression that looks like this: an x bar n plus a naught. Okay. Now again, by induction and previous theorem, this is easy to see. Right? So we immediately got a good collection of examples of continuous functions just by applying the previous theorem. This is a course on real analysis, and you have just watched the module on limit laws.